So we're looking at page 36, numbers 9 and 10. Both of these questions ask us to find the unit tangent vector for a particular vector value function. Right, so in order to find the unit tangent, we need to first find the derivative of the vector value function. So r prime of t. I'm going to write it in component form, with these two being our relevant components. So we're looking at negative a sine of t, comma, a cosine of t. We also need the magnitude. Of those derivatives. So square each component. A squared sine squared of t should look very familiar. A squared cosine squared t under the radical. Clean it up. Factor out the a. We'll factor out a squared. It becomes a when you pull it out all the way. And then the sine squared plus cosine squared is going to equal 1. So it's really just an a. So if I want the tangent vector, the unit tangent vector I should say, t of t, I'm just taking each entry of my derivative and dividing it by its magnitude. So negative sine of t, comma cosine of t. All right. So what we can do very quickly is just have a nice little look at what the unit tangent vector gives us in relation to the original vector valued function. So I'm going to put in constant a, I'll put in a equals 0, creates a slider, gives me some variable radii. I'll open up a set of parentheses to put my vector valued function in 2 dimensions. So a is now defined. So I'll say a cosine of t, close it up, comma, a sine of t, close it up, close it up. The domain here, it is a circle, so 0 to 2 pi makes sense. And I got, there's nothing there. Well, why is there nothing there? Because I have my a value equal to 0, which means I'm working with a circle of radius 0. All right, so how about I make it something not 0? All right, so I'll make it 5. All right, so now I'm going to plot negative sine of t, close it up, comma cosine of t, close it up. Still 0 to 2 pi. All right, and so what this tells us is that for each value of t, we can rely on a corresponding vector tracing out the path created in blue here, the path of this circle, as being the unit vector that shows the rate of change instantaneously of that vector for a teensy tiny change in t. All right. So it's kind of hard to visualize in this sense, but it'll become clearer and clearer as we move forward. All right, so find the unit tangent vector t of t for the parabola traced out by the vector value function, all that good stuff. So I need r prime of t, easy enough, 2t comma 1. I need that magnitude. So 4t squared plus 1 under the radical. There's no simplifying that. But I don't really need to because t of t is just the quotient 2t over the square root of 4t squared plus 1, comma, 1 over the square root of 4t squared plus 1. And again, that's going to be a vector that represents the rate of change of the vector valued function. So a new vector value function that represents a rate of change of the original vector value function for an infinitesimal change in t, but this vector is guaranteed to have a magnitude equal to 1.